Hi, my name is Abigail Russell, and today we are going to be talking about neuroplasticity with an emphasis on multisensory stimulation. The human brain's capacity to change allows it to recover from injury, adapt to new experiences, and integrate information from multiple senses to form stronger connections. This is important because understanding plasticity helps us design therapies for neurological disorders, enhance learning, and can even slow cognitive decline as we age. Before we begin, here are important terms to be familiar with regarding neuroplasticity. Neuroplasticity is the brain's ability to change. Synaptic plasticity is the strengthening or weakening of connections between neurons based on experience. Structural remodeling refers to dendritic growth/pruning or changes in connectivity. Neurogenesis is the creation of new neurons. And lastly, functional reorganization is the shifting which brain regions perform certain tasks after an injury or while we're learning something new. A key point is that although neuroplasticity happens across the lifespan, its timing, intensity, and direction matter. It can be beneficial in recovery situations like after a stroke or when learning a new skill, but it can also be maladaptive in situations like chronic pain or PTSD. To explore how this works in practice, I looked at 3 research articles that examine neuroplasticity through the way the brain forms new synapses through therapeutic interventions with an emphasis on multisensory training interventions. In my first research article, I learned about plasticity-based therapeutics. The aim was to compare traditional behavioral treatments with therapies designed to harness plasticity. The method used included computer-based cognitive training with progressively harder tasks while using neuroimaging to track changes. In using computer-based cognitive training, we were able to integrate sensory information from the visual, auditory, and somatosensory systems. This was beneficial because the computerized training allows high intensity and adaptive difficulty. The findings included improved cognition in aging, brain injury, and schizophrenia. Positive changes also occurred in attention span, working memory, and processing speed. This supported that targeted, challenging, and engaging training that activates multiple senses can drive long-lasting plastic changes. The critical analysis from this research is that there was a good temporal resolution for tracking behavioral improvement, but imaging gives better spatial resolution for seeing structural changes. And the limitation of the study is that effects don't always generalize beyond trained tasks. So by combining therapies, we might receive a better result. In my second article, I studied how synaptic plasticity works. Although this article had a focus on understanding synaptic dysfunction and how that contributes to psychiatric disorders, it also touched on how cross-modal learning accelerates synapse formation. The methods used included MRI, fMRI, PET scans to examine connectivity and activation changes. They also did cellular studies to see synapse level changes. This was paired with pharmacological agents, neuromodulation, and behavioral therapy. The results of the study found that cross-modal integration helps us learn and develop new connections and can impact synapse formation. This can be positive, but also can be negative. For example, those with PTSD have strong neural connections. Their traumatic experiences are often multisensory. This specific situation shows that plasticity can be harmful, and that interventions must be guided carefully in order to not re-traumatize someone or to strengthen these bad thought processes. And a critical analysis of this article was that with an MRI and PET scan, we receive excellent spatial resolution, but poor temporal resolution because we cannot track moment-to-moment changes. And my last research article had a primary emphasis on multisensory integration and neuroplasticity. It aimed at seeing how training modifies multisensory integration in humans. The methods used included the MEG and the EEG to measure mismatch negativity. They also used behavioral training with auto-visual somatosensory tasks, and they also used structural imaging to look at white matter changes. Findings included that training modified responses in multisensory brain areas occurred more than in unimodal regions. Cross-modal training enhanced audio-visual integration but not unimodal processing, and structural changes observed in connectivity pathways. The implications of this include that multisensory and active training is especially powerful in reorganizing the brain. By utilizing our senses and stimulating sense of smell, our visual field, sense of touch, even taste, all of these things, our auditory system, all of these things can help us to develop stronger neural pathways. And a critical analysis of this taught that the MEG and the EEG are ideal for detecting fast neural changes, but have lower spatial resolution. So, to synthesize and compare and contrast these findings, one thing that's important to note is that there were shared findings among all three studies that agreed that plasticity can be harnessed to improve function. They agreed that training, intensity, timing, and multimodal engagement really do matter. Some of the differences or contradictions between these research articles included that some studies emphasize unimodal plasticity and others show stronger effects in multisensory hubs. And another contradiction was that early experience is critical in some cases, like sensitive periods, but other researchers decided that plasticity remains trainable throughout our life. So one of the main takeaways is that we can combine interventions like therapeutic and sensory to yield the strongest and most lasting benefits. By combining therapeutic approaches through cognitive computer-based programs and multisensory experiences, we can help shape neuroplasticity. And one common neuromyth that goes along with this topic is that sometimes people say the brain stops changing after childhood, and these studies help dispel this neuromyth by showing that the brain continues to change throughout our life and that neuroplasticity can happen as we continue to age. In closing, or conclusion, understanding neuroplasticity and multisensory integrations doesn't just expand neuroscience, it also offers hope for recovery after energy, new tools for mental health treatments, and strategies to keep learning and help our brains adapt through life. Understanding more about neuroplasticity will help us as we continue to shape the future in research. Thanks for watching!